Okay, hello everybody. Welcome to a new technical webinar organized this time by Singh Romania Next Generation Network and Singh Canada Next Generation Network. The subject of today's webinar is very interesting and provocative in terms of ideas and discussions, from technology to system stability, exploring nuclear energy's role in modern power systems. I will give you a brief description of the structure of the webinar. In the first few minutes, we will present our activity in NGN Romania and NGN Canada. After that, Mr. Jack Singh will introduce us into the nuclear technology. Here, the topics will be nuclear power market, small modular reactors, and waste management. Following that, Mrs. Doina Ilisiu will give us a presentation about grid inertia, flexibility needs, and the stabilizing role of nuclear generation. Thank you to our speakers for joining us. And without any more detail, I will proceed to the presentation of NGN Romania. We are NGN Group, founded in 2015. We have almost 100 members representing companies from different areas in power systems. We have 17 companies represented by our NGN members. In terms of activity, we organize joint webinars as the one today. We are also at the second webinar this year, and we intend to organize at least one more this year. We organize also expert talks, which are technical tutorials held by experts in power systems on different subjects according to our members' wishes. Also, technical visits all over the Romania's power systems. We usually organize these technical visits combined with expert talks in the field. Last year, we began two interesting and successful initiatives. The first one is Pathway to Power, which are interviews with successful young energy engineers and not just young engineers, but also highly experienced professionals in power systems. And the second one, and I'd say the most beautiful one, is Volta magazine. Volta is a technical magazine. It's the first digital magazine of Sigre Romania, and it's created by the NGN team. It is, as I said, a technical magazine which contains descriptions of state-of-the-art technologies directly from the industry representatives, interviews with worldwide recognized professionals in energy systems, technical papers, and other interesting topics. And last but not least, Regional Southeast European Conference was held last year in 2024 in Romania, Timișoara. It is one of our conferences which we organize one time every 2 years. And since last year, the conference is dedicated to NGN Group, Next Generation Network. The other conference we organize once every 2 years is Condition Monitoring, Diagnosis and Maintenance, which is the greatest international conference of SIGRE on this topic. So I take the opportunity to invite you all at CMDM this year. The call for papers for this year's edition is open by June 15, and if you have papers or if you are interested in the subject of condition monitoring, you are more than welcome. It will be in Bucharest, Romania. And without going into more details, you can follow us on social media and stay updated with our activity, with our events we organize, and all other opportunities launched by SIGRE. Thank you, and I am now giving the floor to Rong.
Okay, thank you, Radu. Let me share my screen. Okay, good morning, good evening, everyone. My name is Rongbo. I'm a power system engineer and transfer solution. Yeah. Uh, a consulting company based in Winnipeg, Canada. I'm also honored to serve as the technical lead for Secret Canada NGN. I'm excited to be here today to briefly introduce who we are at Secret NGN Canada, what we do, and how you, whether you are a student, recent graduate, or young professional, can get involved. Um, like, Within SIGRI, the NGN support student and young professionals in energy industry by connecting early career engineers and researchers to the wider SIGRI community. Our goal is to provide a platform where you can grow technically, build your network, and contribute to shaping the future of the power industry. One of the best way to get involved is by joining a working group. SIGRI has over 250 active working groups around the world. These are small international teams tackling real challenges in power systems. Being part of a working group is a fantastic way to gain hands-on experience, learn from experts, and contribute to important technical publications. Another great opportunity is to write and present a technical paper. Whether you're working on a project through school, research, or your job, sharing your work at a Secret conference, like a Secret Canada conference. We have Secret Canada conference this year in October in Montreal. And even the Paris session is a great way to gain recognition and grow professionally. And of course, simply attending this event allows you to stay current on industry development, meet leaders, and get inspired. To encourage and reward young professionals, Secret Canada offers several initiatives. Every 2 years, we select one NGN member to receive a Paris sponsorship, covering the travel expenses to attend the Paris session. At Secret Canada Conference, we award young members Best Paper Award with 1,000 prize. Students can compete for the Best Paper and Poster Award, which is also 1,000 cash prize. Selected NGNs can also showcase their work on the international stage at the NGN Showcase in Paris with the free registration to the event. To wrap up, Secret NGN Canada is a community built by and for young professionals. Whether you want to write, collaborate, network, or just learn, there's a place for you here. So please join our Secret Canada LinkedIn page and subscribe our NGN newsletter to stay up to the date with all upcoming events and opportunities. Okay. Now I'm pleased to introduce today's speaker, Jack Singh. Jack is the regional sector lead for clean generation and a nuclear lead at Statnec. With a background in chemical engineering, he specialized in nuclear energy, especially small modular reactors. His experience spans new nuclear development, plant life extension, decommissioning, and waste management. One of many highlights of his career includes serving as the technical director for MOTEC, a molten salt MSR facility. Jack has also held roles in renewable energy, oil and gas, contributing in engineering, commercial, and leadership positions. Today, he leads teams and projects that drive secure, clean, and sustainable energy solutions. Please join me in welcome Jack. Okay, I will now hand it over to Jared. Jack, you can start your presentation now.
Thank you very much. So it's a pleasure to be here. Thanks for the invitation to present. We're just going to do a bit of an overview here of the Canadian nuclear industry to begin with. I think one of the key important things to recognize is that we're in a bit of a renaissance here in the nuclear industry, right, across the world. So we've got kind of remits from COP28, which is triple global nuclear capacity by 2050. President Trump last week announced the acceleration of builds, new nuclear projects. And here in Canada, where I'm based in Calgary, Alberta, we're finding that there's a huge momentum that's going on as well. Ontario's recently announced some initiatives. So let's take a quick look at what it currently looks like. These are the nuclear sites across Canada right now. We've got the Bruce units in Ontario at the Bruce Power Site. We have the OPG projects there, the units at Darlington and Pickering, and then we got the Lonely Point LaPro across in New Brunswick. Okay, so you can see they're all CANDU, pressurized heavy water reactors, and a lot of them are quite old. So it hasn't been a new build in a very, very long time here in Canada. So it's the momentum's there in the industry, and what we got coming up in the future are several new projects that have been announced. The main 4 provinces that have committed to looking at nuclear energy here are obviously Ontario, New Brunswick, Saskatchewan, which is not a nuclear province, but have committed to starting looking at nuclear projects, and Alberta, where I'm based, we're just tentatively exploring what nuclear might look like in the province here. Here's some of the proposed projects that we have at least announced, and I'll add one in here as well. So right now, Bruce Power have announced Bruce C site, which is going to be more of a conventional nuclear power kind of technology there. It's not going to be looking at SMRs just because of the power demand they're looking at. You know, they're looking at a total of 4,800 megawatts. That's 4.8 gigawatts. So you're really looking at conventional nuclear power there, right? So we don't know where it's going to be. We don't even really know what the true capacity is going to end up being now, because they're at the feasibility stage right now. It could be a CANDU, the Monarch, it could be AP1000, it could be EPR, it could be anything. NB Power, Point LaPro, they had the Moltex reactor and the arc reactor. Since recent times, the arc reactor is the one they're pointing at, but again, that is all subject to change as well as technologies progress through their design stages. OPG in Ontario, we're all hopefully aware of the BWX300 deployment there, the G Hitachi SMR at Darlington. They got their license to construct last month, so that's looking very positive. That's going ahead. We should also mention at this stage that there's been a further announcement at the Wesleyville site, which isn't included here on the table. And the Wesleyville is 10 gigawatts of power that they're looking at Port Hope in Ontario with OPG as well, right? So we've got a big, big project there that's going to be kicked off at some point, but they are in that early feasibility stage as well. Finally, I work very closely with SaskPower here. So the province of Saskatchewan, they've identified the Estevan site for a BWX300 initial unit and then a follow-up unit as well, which is a small modular nuclear reactor. So the momentum's there, lots going on, lots of plans, but you can see we haven't had a build here in a very long time. So we're looking at some of those projects coming into fruition at some point in the near future. Here in the USA, it's a nuclear power, right? We're seeing all sorts of projects being discussed. We're involved at Statnec with some of those as well. Many of those in the new deployments and new builds that are coming off. So this is a current state of the market there. This is, they got 94 reactors producing almost 100 gigawatts of power capacity. I think it's often lost how much nuclear power is actually generated in the United States of America. It's really important to understand. Texas has just come out and basically said they are a nuclear power as well now, traditionally oil and gas state, but now they're leading a charge on nuclear power here and new nuclear development. And they've got 4 pilot SMRs in development at Texas A&M. So it's a really interesting time. This nuclear renaissance is absolutely amazing for North America right now. So moving on, we've got the upcoming. This is just a bit of a highlight here of some nuclear projects, and there's so many going on right now. It's hard to capture all of them. So here's some key highlights. We're seeing with a bunch of utilities there at a bunch of sites, and you can look at the capacities. We're talking some big projects there again. So it's really important to keep in mind, although the US has been a little slow over the past kind of decade, at the turn of this year, in the last, even 6 months, they've turned to essentially become this powerhouse that's leading the charge here now, especially with President Trump's announcement last week. So what's nuclear energy? Let's do a quick refresh for anyone on the call that might not be aware. Essentially, nuclear technology, nuclear fission technology specifically, is you get fissile material, and you essentially fire a neutron at it. The neutron gets absorbed into that nucleus, and the atom splits. Okay, becomes unstable and splits. As it splits, it releases more neutrons, which go on and then do the same thing. It releases energy in the form of heat, and it releases radiation in the form of gamma and beta particles. So as those other neutrons go on and do the same reaction, you get a chain reaction, right? And you end up having something called criticality. So you can imagine this criticality is 3 more, in this case, neutrons go out into 3 more critical nuclei. They release then 9 more, and it's that exponential effect that gives that criticality. And you can imagine the immense amount of heat that's produced from that criticality. Okay, so that's just the basics on fission. This is what nuclear fuel looks like. So this is conventional nuclear fuel. We have different reactor technology types. If a car uses gas, a truck uses diesel, plane uses kerosene, and a rocket ship uses hydrogen as their fuel. A nuclear reactor uses uranium as the base fuel, right? So that's what a uranium pellet looks like. It's no bigger than your thumbnail right there, right? And they're kind of these pellets, they're ceramic pellets. And some advanced SMRs are now using liquid fuels as well, right? So we're going away from just solid pellets to now liquid fuels in the Gen 4 reactors, which are in development. So none of those have been deployed yet in anger. There's been some prototype test reactors in the past, but the liquid fuels specifically haven't been developed. So in Canada, we have CANDU, which is pressurized heavy water reactor. And that contains some fissile material there. It's mainly natural uranium. Okay, so which is amazing for non-proliferation purposes, and the fact that we have a lot of uranium here in country. We're able to mine a lot of it. So it's very slightly enriched. In the US, you'll find more of the higher enrichment, which is still low enriched uranium, which is 3 to 5% of that fissile material. But now we're seeing a lot of the advanced SMRs and new nuclear technologies. They're using something called HALEU, which is up at 70 to 20% enrichment. So it's really important to understand the different reactor technology types are based on, on the fuel that might go in them as well, right? So here we have the CANDU reactor using natural uranium. What that drives is a technology which then utilizes or requires heavy water here. So D2O. That heavy water is essentially acting as a moderator. So as the moderator goes around in that coolant loop, what it does is it slows down the neutrons that we were talking about earlier with the fission to the right energy level so that it can be captured by the neutrons to go ahead and then maintain criticality. Okay, so that's what's unique. Having the necessity of having natural uranium drives a specific reactor technology type for it to work. If you try to use other pressurized water reactor technology, it wouldn't work, right? Because you're not getting the neutron capture at the right energy level. It's not slowing it down. It's not moderating that neutron enough to get captured. So it produces more energy per kilo of mined uranium. than other designs, but then also produces a much larger amount of used fuel per unit output. So there's pros and cons to everything. There's no perfect solution. It depends on what the needs are and what the requirements are of the operator, right? And that's the key thing. It's like if you have a performance sports car, you don't necessarily want a diesel engine. If you want a high fuel efficient car, you are going to go for the diesel engine. So the reactor technology type goes hand in hand with the fuel. Here's a bit of a comparison between SMRs and a conventional reactor. Okay, so you can see that little person there. That's the reactor core that we're looking at right there. It's significantly smaller than a conventional reactor. You know, they all benefit from being clean, high energy capacity. The differences come in on how you construct these things, how you manufacture and construct these things, right? So because of the size, what you're able to do is a lot of offsite works acceptance testing and factory acceptance testing and qualification, right? You can essentially modularize them off, right? That's what the M in SMR says, modularization. Think of it building the whole unit, the core, or even the balance of plant, some elements of it, constructing that in a warehouse, you know, cold test it, which is no nuclear fuel, right? Do your core testing behind it, check the pressures, check the everything's working, and essentially wind back all the cables, disconnect all the piping, cap them, flange them, get them off, take it onto site, and then hook it up. Because some of the most expensive projects, you know, we're up at 32 billion pounds at Hinkley Point C. Vogel went to $35 billion. That's what happens on conventional projects, because you have to do all of that exercise on the actual site itself, which drives up costs massively. Anything you do on a nuclear site drives up time and cost just because of the measures that you need there, right? You can see there's kind of walk-away safe, passive safety features now, which is really important. You don't need activated control rod systems now, so there's no reliance on shutdown systems and activation of certain things to make it shut down. Some of these technologies actually shut themselves down, self-regulating, and I'll go on to that in a little bit in a while. The cost is significantly less. 1, scale. 2, repeatability. 3, the idea is, again, run it off a production line as you would as a car, right? On a manufacturing line. And some of the reactor technologies will have reduced waste, and we can talk about that in a second as well. So a lot of differences, and again, pros and cons. You do get less power output as you would from a conventional reactor. So here's an example of the GE Hitachi reactor here. This is based on the boiling water reactor designed by GE Hitachi, the big one, the ABWR. And it's just a smaller scale. This is a Gen 3 plus reactor. And the idea here is, you know, you essentially push the water circuit through the actual reactor core, which turns it to steam, which turns the turbine. So you're actually boiling the water using the reactor, okay? The refueling cycle on there, so every time you change the fuel is 12 to 24 months, so 1 to 2 years refueling. And you know, you got a design life there of 60 years. It's 300 megawatt electric, and what that means in reality is that's powering the equivalent of 300,000 homes. Okay, so you can still see, even though it's an SMR, that's a huge amount of energy that you're outputting, and it's stable baseload energy, which is different to kind of your intermittent supplies of solar and wind. We're able to essentially run this thing 24/7 for about 300 and let's say 20 days a year, accounting for plant outage and maintenance time. So massive amounts of baseload power, which is reliable and a high energy density. It's already using a GNF2 fuel, which is low enriched uranium pellets. And this is a Gen 4 reactor, and this is a 100 megawatt electric reactor. The difference here, again, talking about different reactor technology types having their pros and cons, is it's a smaller megawatt electric output, but because it's using HALEU pellets, the refueling cycles are expected to be around about 20 years, 15 to 20 years, right? That's massive. you don't need to replace the fuel on that for 15 to 20 years. It's huge. And look at the temperature. Whereas the Hitachi reactor is, you know, an outlet temperature of around 300 degrees C. The fast neutron spectrum molten metal reactor technology allows this to give an outlet temperature of 510 degrees C, right? So what that becomes directly applicable to is heavy industrial processes. So if you need steam generation for SAG-D up here in Alberta, you know, you need high temperature clean steam, you can get that from one of these reactors. You don't even need to hook it up for electric purposes now, right? You're hooking it up to just provide steam. So that's kind of the different applications you can get for SMRs here. Each reactor technology type will have different applications. And what we have here is you have a core with a HALEU in, the similar kind of metallic pellets that we were talking about, ceramic pellets that we were talking about earlier. And you're pumping molten metal now as your primary coolant loop, right? So that's molten sodium. And then you have an intermediate coolant circuit there, and then you have your conventional steam turbine as a tertiary circuit at the end there. So different reactor technology type there again, different purposes, different applications. So this is the one that I was leading the engineering team on developing, a Maltex reactor. Now here's another crazy design technology development is absolutely amazing that we're able to now essentially use spent nuclear fuel as the feed for a reactor, right? So if you got spent nuclear fuel at all the sites across the USA, the Canada and Europe, you're able to actually recycle that fuel and produce fuel for this reactor. And this is molten salt fuel. So we don't no longer have solid fuel pellets anymore and ingots. What we end up having is molten salt fuel. So the transuranics are actually in a liquid form, and which gives better properties for fission, right? It allows more efficient burn up of the fuel. And then the primary circuit here is a molten salt as well. So that gives better thermal efficiencies, right? It gives better heat transfer properties, which allows a more efficient reactor technology overall. And as we're saying, we can close the fuel cycle. So the output of this, once you end up with spent nuclear fuel of this, goes back into the recycling plant, the sister plant to this, to create more fuel. So you actually burn out a lot of the waste forms that you typically get from a nuclear operation. So really innovative technology, really, really important. Here's a terrestrial reactor. Now this one is really alien to me, but it's a pretty cool thing. This one's actually being deployed now as a pilot test facility in Texas, right? It's been selected as one of those. What you actually have here is the fuel's no longer contained in those kind of sheaths or fuel tubes. The fuel itself is being pumped and recirculated in a molten form, which is really, really unique. So as the fuel salt is being pumped, the core actually is the graphite stays in a steady state, and the fission occurs through that, which is again, it's mind-boggling to me. And then you have your secondary coolant circuit there for the heat transfer across the turbine and generator. So the intent behind this, you know, you're right up there at 200 megawatt electric, but look at the temperature that it's operating at. It's very, very high, very high. And it uses low enriched uranium again, but again, it's not molten. It's all kind of transuranic chloride, and the intent is to replace the whole core in its own right, right? So once the fuel gets depleted, you don't now replace the fuel channels as you would, the fuel assemblies as you would in a conventional reactor. The intent is to replace the entire core, which again is very innovative. It's very, very important. It's it's innovation at its finest that's happening here in the nuclear industry. And here's another one. This is the eVinci Westinghouse micro modular reactor. So now we're at smaller scales at 5 megawatts. And this is important for defense purposes, remote operations, or where you need just a smaller demand. So there's universities that are looking at this as well and just deploying them. And what this uses is a different kind of reactor technology in terms of heat pipe technology. And what we're looking at here is, on the left side, you see all those metallic tubes sitting out. They're the control rods and the shutdown rods. And in the central bit there, the kind of greeny color is that's the core, and you have your fuel within that core. So as as you pull out the control rods, you achieve criticality, which generates heat in that core, and then you use natural convection technology so that the water that's circulating will turn into steam that goes and drives a turbine, condenses, comes back in. So it's a lot smaller. This is supposed to fit on the back of a semi, so it's easily deployable, and it takes up a lot of a smaller footprint as well. It's really, really important that we start looking at all different scales and sizes of nuclear reactor technology. We'll talk a little bit about safety, waste, and cost. These are kind of three of the main areas that I always get asked questions about. What do we do with the waste? These nuclear plants are expensive, and what about the safety side of it? So we'll talk a little bit about safety. As I mentioned earlier, some of the Gen 4 reactors now have, self-regulating, self-shutting down. It's essentially impossible to have a nuclear meltdown, right? Because here's a safety feature, a negative void coefficient that features in one of those reactor technologies there, which is the hotter the reactor gets, the less reactive it gets, essentially. So it's self-shutting down. It prevents the runaway reactions, and you end up essentially having an inherently safe, walk-away safe reactor. You're going to keep hearing this term a lot now as we go into Gen 4 reactors and some of those innovative technologies. So that's the negative void coefficient, and the way it works is you end up with these kind of voids in the form of bubbles, and that reactivity then becomes very inefficient and it shuts itself down. Some innovations, we saw some reactor technologies in TRISO fuel, the eVinci, for example. And this TRISO fuel, that's become the safety element of this now. So as you would typically get those fuel ingots where you'd have the fission products and decay products featuring in the actual fuel, this is contained now within a ceramic bowl. So the fission products are contained within this, and they're tested and qualified up to insane temperatures. We're talking really, really, really high temperatures where they don't melt because it's a ceramic form. So the idea again is the fission products are contained within this, and if it can withstand those extreme temperatures, the fuel itself is inherently safe now. Innovation goes beyond just reactor technology and now into fuel as well. Waste. So we get typical waste forms: low-level waste, intermediate-level waste, and high-level waste, and it's classified as such depending on its heat output and radioactivity, the dose output. As we fission away that fuel, only 10% of it is actually fissioned into the daughter products. The rest of it's actually unspent fuel, right? That's why there's a term of calling it waste form is now used fuel form, because there's a real intent. The UK does it, the US does it, France does it, and you can recycle and reprocess that fuel. You can actually strip away the 10%. And then reuse the 90% essentially. So what is nuclear waste? As we fission away and we split those atoms, that's what the daughter products are. That's what the fission products are. The daughter products are the split atoms, right? That's what is widely known as the nuclear waste. And it's important to understand that there's all sorts of different radioisotopes that are formed here. Those that are high dose have shorter half-lives, right? So those half-lives come right down, but they're very, very active. They're pretty dangerous, actually. So the idea is, as soon as you have nuclear fuel in a conventional reactor, you want to essentially store it in a spent fuel bay in a pond, a giant swimming pool of sorts, for 7 years to let them cool. So that's both cool from heat, but also allow the radioactive components, those really dangerous ones, to decay away, right? So over 7 years, the most radioactive elements, the very dangerous things, decay away. Okay, and then it becomes safer for that surface storage that we'll see on nuclear sites. Okay, so I'm going to quickly skim over these because I know we're getting short on time here. If we were to take all the generation of the US fleet over the last 60 years and put the nuclear waste on a football pitch, it would essentially stack to a depth of less than 10 yards. All that power for 60 years across that entire fleet that we saw earlier is less than 10 yards. That is an immense amount of energy output per waste produced, right? You've got to be really cognizant that that's the case. There's a rendering of it right there. You can see all 60 years of the entire US generating fleet is that's how much waste output, which is not a lot. Here's another infographic here. We're looking at look at that bottle just on the side there. Every year, the UK's nuclear power stations produce 0.84 litres of waste per person. Of that, the high-level waste, which is the dangerous stuff we're talking about, is only 25 millilitres per person. Okay, and that's accounting for all of your energy demands that you would use in a day, from your clothes, from your car, to your TV, to all your devices that you use. That's how much waste per person is produced. It's very, very little. So we shouldn't get worried about nuclear waste of being this stockpile of insane amounts of dangerous material. It's actually very, very small for the energy output we need. Okay, we're going to start getting a little infographic heavy here. So we got energy density. Okay, this is really important to understand. That pellet that I was talking about, just one of those pellets is equivalent to a ton of coal, 17,000 feet cubed of natural gas, and 120 gallons of oil. Just one. On the right, on the left here, we'll see a table right here where we're looking at, if you were to, how many of you use a firewood, and how much heat comes off that? How many use diesel fuel or petrol gasoline in your car? Okay, look at the megajoules per kilogram that you're looking at in each of those. If you compare that to a natural uranium in a fast neutron reactor, that's 28,000 gigajoules per kilogram versus 40 megajoules per kilogram. If you look at natural uranium in a light water reactor, that's 500 gigajoules per kilogram. The energy density, the amount of energy that you can produce from uranium pellets it's orders of magnitude higher than anything else. So it's really important to understand. This is why nuclear is important as our future reactor technology, our future energy technologies. It's very, very important that we continue to develop reactor technology to hit the 28,000 gigajoules per kilogram, because that amount of power is incomparable with everything else, right? So extremely energy dense. So let's translate into a couple more infographics. If you're to power a light bulb with a pound of respective fuel, coal will do that for 2 days, natural gas for 3 days, uranium in a light water reactor, 64 years. Put in an advanced reactor, that's 2,000 years almost to power a light bulb. versus natural gas at 3 days. 2,000 years, right? We'll move on to the next slide. Radioactivity. So this is one of the ones I usually wrap up with because it's a scary word for a lot of folks, right? But I always use this infographic because it's really, really good to put it in context what radioactivity is. So I get a lot of calls from a lot of Statnec colleagues of mine saying well, they live within you know, an area of a nuclear power plant across the United States of America and here in Canada, right? And they get nervous, they get worried. And just last week, I had to pull up this infographic for one of my colleagues to explain to them, look, if you live within 50 miles of a nuclear power plant for a year, you get less radiation, less dose exposure than you would from eating a banana. If you've eaten one banana in the past week or this morning, you've picked up more radiation, more dose than you would if that's how safe nuclear plants are. That's how we design them to be safe. You will not pick up more dose from living within 50 miles of a nuclear power plant for a whole year than you would from eating a banana. How many of you fly? I fly all the time on business. Every time I go through an airport security scan, I think about this. I've just picked up 2.5 bananas worth of dose, right? A dental x-ray, you're into a pile of bananas now. A day on Earth, just living, just spending one day on Earth, you're into the crates of bananas. The flight from New York to LA, you're into several crates of bananas. But that's still not close to living within 50 miles of a nuclear power plant for a year, right? So let's ramp it up a little. Let's look at the average dose of the 3 Mile Island accident. If you lived, if you were within 10 miles of the 3 Mile Island accident, you're picking up that many doses, that many crates of banana, that many crates of bananas there, right? That much dose. Okay. Then let's look at the next accident. If you spent an hour of 2 miles from Fukushima 2 months after the accident, you're into the barrels. So now we're talking about major nuclear catastrophes, incidents and accidents. You're into barrels of bananas now. Still ain't as much as eating 6 months of food. If you eat 6 months of food, you're getting more dose than you would be being within the vicinity of those nuclear accidents. That's how safe our plants are. If you get a mammogram, a CT scan, if you smoke a pack of cigarettes a day for a year, and you're a dose, you're still a less dose of which an increased risk of death from cancer is evident, right? Now we're up in the trucks to get that. Compare that to the nuclear incidents we've just had there, right? The worst one, the single worst incident, and I'm not a fan of HBO because of their series that they put out, that TV show, Chernobyl. But it is important to recognize that that is the worst incident and accident we've had in nuclear since we've had the technology. You know, we're in truckloads, ship container loads, sea can loads of bananas worth of dose there. But when you look at those ships below, that's temporary radiation sickness and not fatal. Okay? When it becomes fatal dose and you're going to die within 2 weeks, you've got huge shipping containers worth of bananas that you need. Okay? That's how safe nuclear plants are, our technologies are. And that's why radioactivity should not be a scary word in any context. So anytime you eat a banana from now on, always know that you've just picked up more dose than living within a nuclear plant for a year. So that's me done. Happy to answer questions a little later. So Jarrett, back over to you.
Thank you so much for that, Jag. I'm now going to pass it to Radu to introduce their speaker, Doina. which then I will stop sharing and pass it over.
Thank you so much, Jack. That was a really impressive presentation. I'm sure we all have a lot of questions and curiosities. Now we have the nuclear technology, and we move to the grid part to see how to integrate it into the network. And I am pleased to welcome and to introduce Dr. Doina Ilisiu, who is a highly experienced specialist in power systems and also a key figure in Romania's power system development. She led the technical control of grid code requirements department within the Dispatch Center, National Dispatch Center, and her work includes key contributions to the development of the National High Voltage Grid Code, the integration of generation units into the grid, especially wind power plants, and she's the author of several national procedures for frequency control and ancillary services. Please, Mrs. Ilisiu, you have the floor.
First page. As I have said, it was very interesting and very good to have a lot of power plants, but the problem is when we try to construct a system and when we try to put in connection all these generation and all the consumers. When we look at this, we look as a conductor in an orchestra, which each of artists know exactly how to play and what to play, and also the context, but it is necessary to be someone to stabilize, let's say, the rhythm, and this rhythm in the system, in the energetic system and the electrotechnic system are the frequency. It's the rhythm of the system in which each part must, each power plant must, and also consumers must follow and be in synchronism in order to have the stability of the sound. So, inertia, it's the second slide. Inertia, it's a parameter very important for the stability of the electrical power system. You know that the frequency, it's the name for the synchronous systems, and that system which are connected in which form on a different an entire system. It's that means that they have the same frequency. In this, the reaction of each rotating machine or the new system, new power generation, have what it is a response to the variation of the frequency, and those is named inertia. That it's this inertia of the system. It's something which characterizes also the evolution and the contribution and the situation of the all contributors of the system. Also machines, also generators, also alternator, which it is inertia of the rotor of the alternator is the most important for giving the total inertia, and of course also the consumers in the smaller contribution, but also they have. You will see in this presentation what means and which is the importance of them. The evolution in actual system, synchronous system, is in in the direction of decreasing the percentage of conventional synchronous power generating module, which have rotating masses and contribute have a good contribution in system inertia. That means they are how to say the base and gives a characteristic of the inertia of the system. If we have much more of them, this conventional synchronous machine, the inertia and the stability of the system for very quickly frequency variation are, let's say, higher. But today, in spite that my colleague has presented before, the direction is to increase the renewable power, renewable source. Those, this percentage of those give have a negative contribution to the inertia of total system. But you have seen also in the development of the European system that a lot of power plant, nuclear power plant was stopped and was give out from the system. That is especially the case of the Germany. And what they have tried to do, they have tried to use the structure of the system which are present in this nuclear power plant and replace them with renewable energy given especially from the north wind power plant from north part of the Germany in the sea. Coming with cables with HVDC, high voltage direct current, and those cables or others form of HVDC also are much more presented in Europe. You know that we have much more than 53 projects of this. What means for inertia this HVDC? That means that we will have in some places in the grid before, which was former the places of nuclear power plants, we will have renewables, but which kind of renewables? Renewables concentrate very good coordinated by HVDC. But what means that is very good for the system stability is perfect, and it's very economical and also in very good engineering. But the HVDC, it also IGBT system in the place when they change the DC in AC. What means that for us, for inertia? That means that they come with the same problem of the high power electronics module. Why? Because they have these electronics, they have not inertia, and that they must do something in order to increase the inertia. What I have tried to say that this inertia is also related, but the decreasing of the conventional power plants, and we must have some others. We must find others. Let's say other solution to have a better response to them. Slide 3. System inertia, it's an essential parameter for frequency stability of the electrical system. Why? Why? Because the system inertia determines the initial rate of change of frequency. That means it's not stop the frequency variation, but determine the rate of change That means the speed of variation of the frequency. And when it's happened, that it's happened only in the case in sudden imbalances, which are between supply and demand, when some trip of source are in place or occur. A slower Rock-off response, I will prefer to use Rock-off because it's a consacrate name for rate of change of frequency, decreases the frequency stability at system incidents as splitting inside of system. Pity for us, I cannot share with you the situation of the three big situation of splitting of the system inside the Europe, the continental system of Europe. Okay, a slower Rock-off might involve a high activation of reserve. That means that if we have a slower Rock-off, that means the activation of reserve are much bigger. That reflects the fact that the new requirements in Europe statuate that the limited frequency sensitive mode LFSME, it's mandatory for all units, also for nuclear power plants. We will see that for that the connection rules for nuclear power plants are a little bit different from before, from 2016, when the new codes, new requirements for regulation are in place in Europe for all the countries. Low inertia decrease also the critical clearing time, that it's very important for the protections. If we have not a good inertia, or the inertia start to be slower, lower and lower, that means that we must to change and to have action for all the protection, also for mine protections, at least at mine protection regarding due to the decreasing of critical clearing time. Also, inertia contribute to risk of corridor tripping and inter-area power oscillation. What is very critical in the biggest system are those inter-area power oscillation, which are a variation of the frequency, very short, with, let's say, period between 0.14 till 0.2 hertz. And if the system are bigger and bigger, those the oscillation as the period of those oscillation decrease. What it means that the frequency, instantaneous frequency can be very quickly, have a rate of change very big, and a lot of units can be lost from the system. And so that to have a good inertia, that means that we can contribute to system stability. The next slide, which are what system like? System like turbo generators. Why? Because they have a natural inertia that provided by rotor inertia for short circuit ratio, excitation, and they have also a good excitation system Salic factor. That means that the turbo generator also present in the case of nuclear power plant have a good contribution on the inertia. Also, in the domain of frequency and also in the domain of voltage. They have the possibility to have this PSS, power system stabilizer, which help the system in case of big perturbation. So main influence, it's also you can see that the typical values of the which cover a wide range of technology are between 3.5 to 8 seconds. And I have give an image of those critical clearing time curve related to external reactance, and of course the value. And you can see that the best value are related in the domain as gas and hydropumps and also as nuclear. We consider nuclear around 6.5 or around 6 seconds. That means a good contribution for inertia, very good contribution for the system. And I repeat, because a nuclear power plant, a turbo generator have contribute not only in frequency of inertia and also in the voltage, taking in consideration excitation system scaling factor and also some apparent power contribution. The next slide. What is sorry for this, because here it was a little bit much more animated, and you can understand if you have interest on better that you can see now on the screen. Situation of this inertia in 2020. It is a situation which I have, but I can say that it's an optimistic situation. Because now the influence and go out of function, out of operation of a lot of classical units have decreased the inertia. You can see with red, that means the countries which have a limited contribution to inertia, in which country, and those countries need to take actions to increase and to have increase a contribution to inertia, and also to have and to provide other solution for good responses for rock-off. We can see that Romania has had at this year a good contribution. Of course, probably now the contribution is less. You will see what it's happened. And I can say, first one is the top of the slide. It's a slide regarding the estimated inertia for Romania as percentage of hours in a year. I say you can see that it's starting at 5 seconds, and they finished at 1, and as percentage as hour. But that is a good one. The better one is coming from France, because in France, you know, they have a lot of nuclear power plants, and you can see how very good curve they have. The minimum, let's say approximately 99 of hours, 99% of hours per year, they can contribute to the system with 3 seconds with a good, very good inertia. You can see that the maximum value is 6 that it's provided. I repeat, for the nuclear power plants. That means the nuclear power plants are very, very important in the system. What to say about Germany, which have lost a lot of power plants? We can see that it's a car which very quickly at 80%, they decrease under 1. And now I have give some tables at the level of year 2020 with difference value of the inertia for different countries. And you can see the situation. Of course, the situation it's related in the lower related to the percentage of classical units in the system. You can see above in the last part of the screen also for the others system, synchronous system as Baltic, Nordic, and of course Ireland and Great Britain. The next slide, it's how to calculate the inertia. It's a formula, and it is related of the rated frequency that, of course, from 50 or 60 hertz, and is related, you can see, in the apparent power, the momentan apparent power of the total system and momentan apparent power of the synchronous generators, and also is direct proportional with the imbalance of megawatts. When this imbalance of megawatts can lead to a big variation of the frequency. And the Rokov, it's also related with the total kinetic energy of the system. And the next slide, it's related, let's say, much more clear how on the effect which we can follow and we can identify very, very quickly, very easier regarding Rokov influence. That means the Rokov, it's total points. That means it is how quickly the frequency it's going down. Here we have a loss of generation, but I repeat, is not Rokov. The Rokov has not an influence and is not the cause to stop frequency. The stopping of the decreasing of frequency is done only, but only by the reaction of the variation of the frequency. And with other words, we say that we must not lose units and generation when we have a big Rokov, that it's mandatory, that is asking for all units to stay connected. This variation of the frequency of the rate of variation of the frequency, but the stabilization of the frequency is provided only by units which contribute by increasing them power. And for that, of course, one of very important units are nuclear power plants. Okay, the next slide. What it's happened. Knowing this and having information on this, some regulation at the European level, it was focused on the ideas that each TSO and at the level of all TSO, it's mandatory to calculate them inertia at least from 2 years in 2 years. And to evaluate them inertia, because in other ways, some incidents can occur. And of course, it's also mandatory for ENTSO-E and for all TSO to establish a minimum inertia needed for the system. That means how we contribute to this inertia, it's of course by the units which have a good contribution, but also with other measure for all the units connected by electronic. And we will see in the next slide. But no, I remain at this side saying that in Europe we have a dedicated monitoring system that it's WAMS, that it's a wide area measurement system, which have based on PMU, based on measurements with less than at minimum 20 milliseconds, in order to know exactly and to have a prevision to forecast if something of the rock-off will happen. That is as a level of the TSO, and at the level of the generating units, the same regulation commission has issued requirements for generation for connection, and those each generation must have some requirements also for synchronous units and also for PPM. The next one, it's the requirements for rock-off. That means that to make face to this rate of change of frequency, the units must be stable, must remain on the grid for some curve, some standard curves of frequency deviation, frequency variation rock-off, that and you can see on the screen with red and with blue. And those possibilities, those features, those soft and hard implementation at the level of the units of, especially for PPM, because the nuclear power plant have intrinsic inertia, is named grid forming. That means it's named grid forming in sense that all the device must have this contribution, must provide this contribution. It's accepted in the grid only if they demonstrate that they are capable to make face to rock-off. That means to have and to increase a synthetical inertia for the system, increasing the natural inertia of the system. I can say also that we have two kinds of requirements for generating this grid forming and also grid following. Grid following is related to the contribution of the variation of the frequency as LFSMA and FSMA, I have say, which is also required for nuclear power plant, but those one grid forming is not required for nuclear power plant because they have intrinsic inertia, but is required, yes, for the HVDC, which are, let's say, coming exactly in the former place of the nuclear power plants, but for all HVDC. Regarding the nuclear power plants, their requirements is to assure the 1 Hertz per second as rock-off and stay connected to the grid. It's not required too much at 2 Hertz because there are the difference for the pole. It can be too difficult for the rotor of the alternator. And to have this equipment certificate in which this unit provide that is capable to support, to have contribution for 1 Hertz per second, the units must assure limited frequency sensitivity mode and also frequency sensitivity mode, and that must be provided all the time. That it's for us in Romania, it's a problem because the older units have not those possibilities. They have only the inertia, inertia, but LFSMA and FSMA is provided for all the others, for many of others nuclear power plants. And also the nuclear power plants must assure a flexibility. That must assure a flexibility day by day and week by week. That means that can operate at different point of function of operation. Not very quickly, not very often, but they can have flexibility. And that is the biggest requirement regarding the nuclear power plant. And this needed because we have less and less inertia. Some conclusions. ROCOV maintain to provide ROCOV, it's in the scope to maintaining a sufficient inertia. Also, power electronics converters based on device must have devices with grid forming capabilities and also grid following, and that must be provided for all generators or batteries or HVDC which are connected to the grid by electronical. Grid forming inverters mimic the behavior of the synchronous generators. The amount of inertia the system must be estimated by the TSOs. And this monitoring of inertia must be also provided by WAMS. I can say that are the main requirements on the nuclear power plants. They are not very difficult. From my point of view, there are only related, or the main are related to, let's say, the flexibility and to stay connected, because they have a big contribution in inertia of the system. And what I want to add is the fact that the biggest ROCOV we can see during the splitting of system, and you know all the splitting of the Iberian Peninsula last month. I can say also that this inertia, the lack of inertia, can also lead the operators of system to imagine and to open the door for new reserves which are capable to limit this ROCOV. And what to say, we need nuclear power plants if they are safe, and they are safe, you have seen, I believe in it. And we are very happy to have it as system operators from point of view of inertia. Thank you.
Thank you, Mrs. Ilisiu. Thank you so much. It was a very insightful presentation. And now I'm giving the floor to Jared for the Q&A session.
Awesome. Thank you, Radu, and thank you, Doina, for that. So just in the interest of time, we do have a Q&A session afterwards. If anybody has any questions, feel free to put them into chat, or if you want to raise your hand quickly, you can ask questions to both Doina or Jag. I'll leave the floor open for a little bit. I'll see if I see any questions. Also, feel free to just unmute your mic and speak if you guys have anything. I know it's a lot of information, so yeah, it could be left for words if it was a little much. But
Jared, in Q&A session, you see this is from Norma Field. He left a question.
Oh, okay, I see. So, okay, so Norm, I can just read your question. Norm's actually from Statnec, a good colleague of mine, but he said the EPA has dozens of Superfund sites across the USA to clean up radioactive waste created from nuclear reactors. Is this a consequence of old reactor technology or material handling procedures that would not be repeated with current technology and procedures? I think that would be more for you, Jag.
Yeah, so it really depends, right? So if there's some kind of radioactive spill out or kind of contamination or things like that, then you can have some of those remediation activities, right? Typically, as we were talking about in the presentation there, spent nuclear fuel will come out the reactor core, go straight into a pool, spent nuclear fuel pond, and then it's stored there for 7 years. After that, it'll be like kind of packaged up in that swimming pool area, and it gets placed into casks, and those casks will go onto basically some silos on site for a dry store. So you get the wet store and the dry store. So we typically, when you see those kind of cleanup activities and those contaminations, it's not related to that, generally speaking. That'll be related to kind of other things. Because there's not just nuclear generating sites, there's nuclear labs, for example. There's nuclear research facilities. Like I was saying, there's universities that are exploring this. There's also all sorts of different radioisotopic applications, right? So neon lights, for example, is a classified nuclear facility, right? Production of neon lights. That might draw a license application there. Or if you're producing nuclear medical isotopes or handling nuclear material in that sense, you might have it. So there's a whole bunch of different things that may trigger something like that with the EPA, where you have to sort of clean up and remediation if there's been some contamination leaks from those kind of sources as well, right? So it really depends on which site it is, really depends on what's being done at that site, and it depends around the specific context behind where those radioisotopic materials have kind of contaminated that land. That's typically where you see those. So I know it's not the clearest answer, but it's such a broad subject. It could apply to a lot of different things.
Awesome. Thanks for that, Jag. Okay, I'm going to look in the Q&A one more time. So I don't see any more questions. I will open the floor one last time, but
I have a question, actually.
Sure.
I have a question for Mrs. Ilisiu about the inertia estimation techniques. From your experience, if you know if any TSO uses real-time inertia estimation techniques, and if these techniques are helpful for preventing large outages in the network.
So I don't know. I didn't see exactly the evaluation technique of the TSOs to evaluate and to say exactly the value of the inertia. That it is a wish, and it is written in the recommendation, but they are not, in fact, let's say, very deeply analyzed. We try to analyze only in some situation, in some moments, in which the differences as a percentage between classical and the new units, the renewable units, units connected by electronics power module, they to evaluate the variation of the inertia. Regarding the fact to if they can prevent the blackout or something huge situation, that it's only one element. It's to monitor the frequency and to see if some especially inter-array oscillation start. I have seen a lot of inter-array oscillation starting even if some bus bar or some actions in the let's say points of the system, the recharge and the changing the topology is coming. It's have done, and those are starting, but also was stopped very quickly. It depends of the type of oscillation. For this, of course, we have an international system, it's WAMS, but usually we use this WAMS system especially for after incidents, for analyze of the incidents. The actions and a lot of SIGRES papers, as the latest one in which I have collaborated, is to impose and to promote the idea to use WAMS system inside the MSS SCADA in order to have actions on those oscillations. That is for the moment only wish there are, but this time of WAMS and PMU are present in islands as examples, and or in some isolated system that are present, they can help and can take actions. But for, let's say, as Romania, we have not for the moment. But we have a lot of PMU, with especially that it's for all the countries in the interconnections lines for the tie lines for connections between different systems. And also for the biggest station in which are connected only renewables. I don't know if I have responded to your question, please say me.
Yes, you have. Thank you very much.
Awesome. Okay, thank you, Doina, for that explanation. Oh, looks like we have one more. Adrian, this will be our last question, then we'll wrap it up here.
Yeah, okay. Thanks a lot. Thanks a lot, Jared. I do have a question for Mrs. Ilisiu. Mrs. Ilisiu, considering the recent events that we had in the continental Europe grid with Iberian Peninsula blackout, and also considering the public data which is, let's say, available, which is the role that inertia played in what happened? Which is your expert opinion on that?
Firstly, it's important to have the final report from the NSOE, because they have a lot of good specialists, and I know one of them. It's a specialist also in inertia, and probably Giorgio will say much more about this part. But indeed, I appreciate that inertia is in the decreasing at the level of each country. And what I can say that the rock off, which I have measured, but okay, only that it's my evaluation, it's subjective. I have seen that it was 2 hertz per 3 seconds. That for me, this rock off was not very, very high. I didn't see the real or the public variation of the frequency, both in Spain and also in the other part of Europe, to be very clear at which was this rock off at the moment of splitting, because usually the biggest rock off occur in the moment of splittings of system, and we have this experience. For me, it's what I have seen there was a lot of inter-area oscillations, and in my opinion, that are very, let's say, difficult to be stopped or to be mitigated, and that can be one of cause. But I'm not in for the moment in this implied in this analysis. It's better to see the site of ENSOE when ENSOE will publish the physical situation of the real situation of this big. But of course, to have less and less inertia, that it's we must be aware that we must have also countermeasures. If something occur, that means as engineers we must find other possibility to stop and mitigate the phenomena. That is our role.
Awesome. Thank you for that, Doina.
Thank you.
Thanks for that question, Adrian, Norm, and everybody who was all here today. First, I want to also thank our speakers, Jag and Doina. You guys clearly have a lot of technical knowledge and shared a lot with us today. So I'm sure a lot of us can take some key points with us. And yeah, I know people from Romania, it's dinner time for you guys. So you guys are probably hungry. And some people out here in North America, this is kind of mid-work day. So I really appreciate all you guys taking the time out of your days to join. If you guys have any questions, feel free to reach out to NGN Romania or NGN Canada. And yeah, for upcoming events, whether that's online networking events, more technical webinars, or anything that we have going on, please make sure to subscribe to our newsletter. We have a bunch of events coming up for the Canada NGN. I will speak for us, and I know Romania always has a bunch going on. So yeah, stay connected and we'll keep in touch. Thank you guys all for coming out.
Thank you. Cheers.
Thank you, everyone.
Thank you. Thank you very much.